All right, let's dive right into this explainer. We're going to build a map of how everyday matter transitions between solid, liquid, and gas. And of course, we'll look at the wild exceptions that completely break all the rules. When we look around, matter seems pretty stable, right? Ice is hard, water flows, and the air is just there, invisible. But the truth is, the physical state of any substance is really just a temporary condition. It's completely at the mercy of its environment. So today, we're going to unpack exactly how that whole process works. Here's our roadmap for today. We'll start with the three states of matter, then check out melting and freezing points. After that, we'll compare evaporation versus boiling, dive into the sublimation exception, and finally, look at how pressure changes absolutely everything. Okay, part one, the three states of matter and the fundamental rules. So looking at this overarching flow chart, it's pretty clear how big shifts in temperature cause massive physical changes. We've got solid at the bottom, liquid in the middle, and gas right up at the top. The red arrow on the right shows that as we crank up the heat, we drive the state from solid to liquid through melting, and then from liquid to gas through either evaporation or boiling. And obviously, lowering the temperature reverses the whole journey. It brings gases back to liquids through condensation and liquids back to solids through freezing. It's just a beautifully balanced system. Moving on to part two, melting and freezing points, which act as our thermal boundary. Now, the absolutely crucial thing to remember here is that for any given pure substance, melting and freezing happen sharply at the exact same temperature. It's totally a two-way street. The temperature where a solid turns into a liquid, that's your melting point. And the process completely reverses at precisely that same temperature if you cool the liquid down, which we call its freezing point. Take pure water, for example. It completely respects this rule. It's going to melt from solid ice into liquid water suddenly and sharply at exactly 0 degrees Celsius. And if you take that same liquid water and cool it down, it freezes right back into a solid at that exact same temperature, 0 degrees Celsius. The melting point and the freezing point are literally identical. Okay, part three, evaporation versus boiling. Let's look at that liquid to gas transition. People use these terms interchangeably all the time in everyday conversation, but scientifically, they behave very differently. Evaporation is strictly a surface-level event. It happens when a liquid changes into a vapor at a temperature below its boiling point. Basically, if you just leave a liquid with its surface exposed to the air, it evaporates. And the larger that surface area, the faster it happens. Warmer temperatures speed the whole thing up, too. A really great example from our sources is the Dead Sea. Because of that exceptionally hot climate and its massive surface area, the water there evaporates incredibly easily, which is exactly why it leaves behind a notoriously high salt concentration. And this breakdown brilliantly illustrates the contrast. Evaporation is a slow, surface process that happens over a wide range of temperatures. Boiling, on the other hand, is a full-body transformation at a precise breaking point. When a liquid hits its boiling point, it gets hot enough for gas to actually form within the liquid itself, not just sitting on the top. That's exactly why you see bubbles violently appearing deep down inside a boiling pot. Before we really dig into the mechanics of boiling, I've got a quick question for you about something you probably have in your kitchen. Think about a boiling kettle. Is the white cloud escaping from the spout actually a gas? It's kind of a trick question, but it reveals an incredible, invisible truth about matter. Check out the glass kettle on the left. We can clearly see boiling in action, right? Bubbles are forming all throughout the liquid. But now, look at the metal kettle on the right. Notice that clear, totally empty gap right at the mouth of the spout? That is the true gas. Colorless, completely invisible water vapor. That visible white cloud of steam you see floating further out, that's actually liquid water. It forms through condensation when the invisible vapor hits the cooler air and turns back into tiny droplets. So the gas state of water is actually completely invisible to the human eye. Pretty wild. Now keep in mind that not all liquids boil or evaporate at the exact same rate. And that brings us to the concept of volatility. A volatile liquid is simply one that evaporates easily. This happens because the intermolecular forces, those tiny magnetic-like poles keeping the liquid molecules clustered together, are just very weak. Comparing water and ethanol shows this principle perfectly in action. Water has a relatively high boiling point of 100 degrees Celsius, which means it has stronger forces holding it all together. Ethanol, though, has a boiling point of just 78 degrees Celsius. Because it takes significantly less heat to break those molecules apart and turn them into a gas, ethanol is much more volatile than water. All right, part 4, the sublimation exception. Let's talk about bypassing the liquid phase altogether. So, we've learned the rules, but nature absolutely loves an exception. A few solids completely ignore the liquid phase when they heat up. Instead of melting, they just jump straight from being a solid into a gas. It's a really fascinating process called sublimation. The liquid phase is just entirely bypassed. Take a look at this block of solid carbon dioxide. We usually call it dry ice, and it totally earns that name because there is absolutely zero thin film of liquid water on its surface like you'd see on a normal ice cube. At normal pressures, it doesn't melt at all, it sublimes directly into a gas. And just like our kettle example earlier, that thick, dramatic white smoke you see pouring off of it, that isn't actually the carbon dioxide gas itself. It's made of water droplets condensing from the surrounding air because the dry ice is just so incredibly cold. Finally, part 5. How pressure changes everything. This is the ultimate hidden variable. So we normally define a boiling point as a specific temperature, but it actually comes with a really strict condition. A liquid only boils when the high-energy molecules inside it manage to create a pocket of gas, a bubble, with a pressure that perfectly matches the atmospheric pressure pushing down on the liquid from the outside. If the atmospheric pressure pushing down changes, well, the temperature required to push back and create that bubble is going to change too. So the boiling point of water is 100 degrees Celsius, sure, but that value is strictly tied to standard pressure, meaning the pressure of the atmosphere right at sea level. This means if you, say, climb a high mountain where the air is thinner and the surrounding pressure pushing down on the water is lower, it becomes way easier for those gas bubbles to form. Because of that drop in atmospheric pressure, water on a high mountain will actually boil at a temperature much lower than 100 degrees Celsius. So I'm going to leave you with this final thought for today's explainer. We just saw that if less pressure makes it easier to boil, the boiling point naturally drops. But what happens if you go the complete opposite direction and forcefully increase the surrounding pressure? How wildly hot could liquid water get without ever turning into a gas inside a super high-pressure environment, like, say, a boiling deep-sea volcanic vent, or even just the pressure cooker sitting in your kitchen? Think about that the next time you boil a pot of water.